So we're going to look at some examples of calculating beta hat using the matrix formula that we just derived. So we're going to do a couple of quick examples. The first example assumes that we just have a constant mean. So it's actually a little bit of a simpler model than what we normally have been doing. In simple linear regression, we assume that we have an intercept and a slope. With this model, we essentially assume that there's just an intercept. So the first example here, we're going to assume that the response is equal to some constant mean. So it's not a function of any changing regressor variable plus the error, which means that our x variable is just 1. So for each observation, there's just an intercept. There's no covariate information. So x is equal to 1, and this is the same as beta equal to mu, where there's no beta naught and beta 1. There's just a beta. And so what this would look like actually, this kind of data would be something like this, where there's no trend. And so we just want to fit, that's not very good, a straight line to the data. So that's what we are assuming that we want to do with this kind of model. But we can still use this matrix formula here. So we have our responses y1 down to yn, and they're equal to a mean that's constant for all the observations, plus our vector of errors. And we want to represent this in matrix notation, so using x beta plus epsilon, okay? Which means that x, in this case, is just going to be a vector of 1s, a column vector of 1s, and beta is just a 1-by-1 matrix mu. And if we did the matrix multiplication, then it would simplify to what we have up here. So assuming that model, the question is, what is the least squares estimator of our regression coefficients, or in this case, regression coefficient, just a single one. So we go back here, and we have our formula x transpose x inverse, x transpose y. And if you do the matrix algebra here, we get y bar. But I want to show you, or at least try to convince you, that this is in fact true. So we have that in this particular example, x is equal to column vector of 1s, right? And then y is just our usual vector. And we want to compute x transpose x. Sorry, writing on tablet's not easy. X transpose x inverse, x transpose y. And so if we do x transpose x, we have a row vector of 1s multiplied by a column vector of 1s. Okay, so this is x transpose x. So x transpose x equals this. And so we're just going to get 1 times 1 plus 1 times 1 n times. So we just get n, which means that x transpose x inverse is just 1 over n. And then x transpose y is going to be that row vector of 1s multiplied by that column vector of the responses. And so we're going to just get y1 plus y2 all the way up to yn, or in other words, we're going to get the sum of all the y's, which means that x transpose x inverse x transpose y is just going to be 1 over n times the sum of the y's, which is y bar. Okay, so what that means is that if we're fitting a constant mean model to our data, then our best estimate of the intercept or of the regression coefficient is just the sample mean, which is obviously very straightforward to calculate, pretty easy. And in R, to calculate beta hat, we would just do mean of y, where y is a vector that contained all of our responses. So that's a very simple example, but now we can move on to a slightly more complex example. And actually, I guess this graphic right here shows a constant mean fit to some data. So this obviously isn't a very good fit, but I generated some data here. And if you just take the sample mean and use that as your estimate of the constant mean for the data, then you get this horizontal dashed line running across the screen there. Okay, so now let us assume a simple linear regression model instead. which means that our X matrix is going to be a column of ones and then a column of X values. So for saving space on the slide here, I wrote it in a kind of unusual notation, but I'll rewrite it on the note sheet there. And then I've pre-computed a few different quantities for convenience, just because it's not obvious that you're going to get this. So I've computed X transpose X here, and so if this is your X matrix, and you do X transpose X, then you're going to get a 2 by 2 matrix where the first element here is n, then we get the sum of the x's and the off-diagonal elements, and the second diagonal elements is the sum of xi squared. And if you invert that, then, which you can actually do in closed form expression pretty straightforwardly actually, then it simplifies to this. Okay, so this is a simplification of X transpose X inverse. I've actually rearranged some of these quantities, but this is X transpose X inverse that we'll use. And then X transpose Y is going to be the sum of the Y's and the sum of X's multiplied by Y's. And so what I want you guys to do is I want you guys to pause this for a few minutes, however long you need, and do the matrix algebra and see if you can't obtain on your own the estimates of beta naught hat and beta 1 hat in this particular setting. And then unpause it, and then we'll look at the solution together. Okay, well, hopefully that went well for you. In case it didn't, or in case you want confirmation that you did things correctly, we're going to work through this example together. So, as I mentioned, so our X matrix here is a column of ones that corresponds to the intercept, and then our column of predictor values x1 to xn. So that's our X matrix. And then we basically need to multiply everything out. So that's already on the previous slide, but I'll write it here just for convenience. So we want to compute X transpose X inverse X transpose Y. And using the information on the slide we were looking at, we have 1 over n plus x bar squared over the sum of xi minus x bar squared. And our other element here, I'll write that down. Guess I need a little bit more room, don't I? So the off-diagonal elements are the same. And our last element here. Okay. So we have that matrix multiplied by the sum of the y's and sum of the x's times the y's. Okay, so we have to do this matrix algebra, and it's not terribly difficult, but we definitely have to be careful and try not to make any mistakes here. Okay, so we're going to start off with this first part. So with this matrix algebra here, I want to multiply this element by this element over here, and then I guess I'll use this. And then we want to add to that this element multiplied by this element right here. Okay, so what I'm going to get is I get the sum of the y's over n plus the sum of the y's times x bar squared over the sum of xi minus x bar squared plus, I guess just say minus, right? Because we have a minus right here. So minus x bar times the sum of the y's over the sum of xi minus x bar squared. Oops, I guess I really just made a mistake, didn't I? Sorry about that. So the first part is right, so minus x bar, but I'm going to be multiplying that by the sum of the x's times the sum of the y's. Okay, so that's the first part there. And then I need to multiply the second element. So let's see if I can, well, it doesn't want to do that. Okay. All right, so on this bottom part here, I need to multiply this element times the top element here, and this second element by the bottom element there. So I get minus x bar times the sum of the y's over the sum of xi minus x bar quantity squared. for the second part here, I'm going to get 1 over the sum of the xi minus x bar squared times the sum of xi yi. Okay, so we've done the matrix multiplication and we need to simplify things a bit. So I'm actually going to start in the bottom just because I think this is going to make a little bit more sense if we do it that way. So we see that they have a common denominator, which is nice. We have the sum of xi, yi, and I have this x bar here, which I don't like. So I'm going to move this part to the front and move this part to the back and put everything over a common denominator. So I get the sum of xi, yi minus x bar times the sum of the y's over the sum of xi minus x bar squared. I'm going to keep simplifying here. This is the sum of xi, yi. And since x bar is just 1 over n times the sum of the x's, I'm going to factor out that 1 over n and get the sum of the x's times the sum of the y's. And it's not too difficult to show that this denominator is actually the same as the sum of xi squared minus 1 over n times the sum of xi quantity squared. So I'm going to do that. And if we compare that to the work that we've already done back when we were doing simple linear regression, we can see that this is actually just beta 1 hat. Okay, so that looks good. So the intercept that, or the slope that we derived was actually just beta 1 hat, which we had previously derived using a different method. So that's great. And now we need to look at this top part and see if we can't reverse engineer that intercept. So this is a little bit more complex expression, but we can rearrange this to make it not look too bad. So I have the sum of the y's over n here, so that's just y bar. And I have a common denominator here, but for strategy purposes, what I'm going to do here is I'm going to factor out this x bar with a negative in front. And so I have y bar minus x bar times the sum of xi, yi minus 1 over n times the sum of the x's times the sum of the y's over the sum of xi minus x bar quantity squared. And so where did this stuff come from right here? So I have x bar squared up in the numerator. I factored out one of those x bars. Okay, so I'm left with a single x bar, but as we've already noted, x bar is just 1 over n times the sum of the x's. So I just factored out that 1 over n, and so I get the sum of the x's times the sum of the y's. But then if we compare that to what we were doing just below, we see that this is exactly what we had before. Okay, so this is actually just beta 1 hat. So this is y bar minus x bar beta 1 hat, which is the formula that we had previously derived for the slope. Okay, so what does this practically mean? All right, you probably are thinking right now, well, great, we worked through the matrix multiplication with matrix algebra. What exactly does that tell us? So using a simple linear regression model, using straightforward calculus, we derived the estimator for the intercept and for the slope. Okay, and then using matrix notation, we derived a separate formula for how to quantify or how to estimate beta naught or beta hat in general, right? X transpose X inverse X transpose Y. And so what I was trying to show you is that really simple linear regression is just a special case where we're using that matrix notation for computing our regression model. And so as long as we set up those X matrices appropriately, then the results that we had previously derived are just special cases that are obtainable using the matrix algebra. And so what we have shown is that if X is equal to a column of ones, and the second column is the values of our predictor variable or our regressor variable, then the solution that you get for beta hat is just beta naught hat beta naught hat, and beta 1 hat, which is exactly what we wanted in the first place. Okay, so we showed that using matrix algebra, we were able to obtain the results that we had previously obtained using matrix calculus. And then here, I showed an example where how would we actually compute beta 1 hat and beta naught hat in R. And so we're assuming that x and y are the vectors that contain the responses, and then x is actually just the x value. So it's not a column of ones, it's just the x values itself. And so I'm multiplying the x's and y's together, adding them together, and I'm subtracting the sum of the x's times the sum of the y's divided by n. I'm dividing that by the sum of the squared x's minus the sum of the x's squared divided by n. And once I have beta 1 hat and I obtain that, then I can use that same formula to compute beta naught hat, which is just the mean, the sample mean of the y's, minus beta 1 hat times the mean of the x's. And so we can compute these pretty straightforwardly in R as well, just using a few simple commands. And looking at the fits of my estimated regression line to that simulated data set, we see it looks pretty good here. It's sort of what we would expect to see if we were just going to draw the line that fit best using our eyes. So we did 2 examples. You may be wondering, well, why don't we do some more? And the reason is because once you get past 2 dimensions, you can't really do these computations in nice, convenient, closed form expressions. You need a computer to do the computations. So from here on out, for the most part, we're going to let the computer do the hard work and compute all these things for us. And the problem that we're going to face is trying to figure out what model to actually fit to our data sets. Because there's a number of models that we could fit, we want to do the model selection in an intelligent way that gives us good results for the problem at hand.